It's time MPLS was made to do the multicast heavy lifting in our core. Welcome back to the MVPN video series. In this video, we build upon the concept introduced in video 6, that is how to build an SP multicast core using MPLS as opposed to IP. That's right, we once and for all get rid of PPIM, leaving us with only one instance of PIM, that would be CPIM, the customer PIM, to worry about. But why do this? What are the benefits? Why should one learn and implement something new? And the old solution really works. It has worked for almost 2 decades at this point. Well, let's enumerate some of the benefits. The first benefit is really streamlined configuration. The reason for this is that now both the control and forwarding planes for unicast as well as multicast traffic are unified. So previously, even though the VPN unicast traffic was utilizing MPLS as a forwarding mechanism, the MVPN multicast core still had to rely on mGRE, which, as you know, is IP-based. Now, with MPLS, we can use MPLS really for all forwarding, and we eliminate IP further from the core. So number 2. We inherit all of the other capabilities of MPLS that we are already familiar from in unicast MPLS forwarding. One example of this would be MPLS fast reroute, which can now be used also for multicast. Finally, we reduce and minimize more state in the core by getting rid of PPIM, like I mentioned earlier. PIM is a soft state protocol which needs constant refreshing, and we have demonstrated in earlier videos that while using source-specific multicast or data MDT enhancements, we can reduce some PIM state in the core. We are still left with an enormous amount of state per MVPN on all core devices that are in the forwarding path. With MPLS and MLDP, because it is TCP-based, that is going to be a major benefit. Now that you know about the benefits of MPLS-based multicast, let us take a look at one possible implementation which allows us to use the knowledge that we already have acquired from watching the previous videos of this series. Well, you did watch the previous videos, didn't you? But jokes aside, with this video I am assuming 2 things. First, I'm assuming that you understand how classic Rosen or, Rosen-GRE or MDT-GRE or Profile 0 or whatever you choose to call it, you know how it works. I'm assuming that. Secondly, I'm assuming that you know how MLDP functions. At a very rudimentary level, but you know how MLDP functions, what are MP2MP LSPs, what are point-to-multipoint LSPs, you're aware of all of that. Because if you're not, then this particular video is really not going to be that much beneficial, and it's not going to make much sense. If you do not meet this criteria, the previous videos in this series, they conveniently cover both of these topics. Plug. For Rosen-GRE, you can watch video 1 and the first half of video 2. I think that's going to be more than sufficient to bring you up to date as to what we are going to talk here. For MLDP, watch video 6 in its entirety. So all 3 of those things, they're going to bring you enough knowledge to comprehend what I'm talking about here. But for those of you who are familiar with these concepts, you've done your homework, bravo. Let us refresh what the previous components of Profile 0 or Classic Rosen were. So in Profile 0, one of the first things to know was how are the CEs or the customer sites going to exchange their multicast states, which is very important, with the provider sites. In the vast majority of all cases, including Profile 0, this is almost always going to be done with CPIM or customer PIM. Now, customer PIM is just regular PIM that the customer is running that has been extended over to the provider, but the provider doesn't accept those packets in the global PIM because that would cause chaos. So the provider on the PE routers is going to run VRF-aware PIM, and it takes those PIM states from the customers and it only refreshes or only adopts those states into the VRF-aware table on the PEs. The next thing is, how are the PEs, so PE1 and PE2 in this particular case, how are they going to exchange these customer states with each other? Because that's the whole idea, to get the multicast state across the core. In Profile 1, they were simply exchanging the CPIM states using CPIM packets with each other. So any packets, joins, hellos, etc. that were received from the customer, the PEs were exchanging those with each other. How they do that, that was the interesting part in Profile 0. That is what gives Profile 0 some of its other components. So the first thing, how are you going to transport those CPIM packets? That was going to be mGRE. So it was IP-based forwarding, and we were using multipoint GRE tunnels to encapsulate the CPIM packets and get them from one PE to whatever other PEs that those packets needed to go to, whichever other PEs needed those states. The signaling is also important because you have to create the tree for the transport inside the core. So the transport is multicast, and you have to create a tree for it. So how is that tree going to be signaled? In this case, the easiest way to do that was to use provider PIM. Now this is the global PIM that all of the Ps, all of the PE routers are going to run. And that was, as we saw, that created a lot of states. That's not one of the benefits of Profile 0, but that was one of the cons of Profile 0. Now, how do we change this to provide MPLS-based forwarding? What do we name it, and what are some of the new components? So there are many different ways of providing the same thing. But in this particular case, we are covering something that is called Profile 1, right? So Profile 0, now you have Profile 1. And it is also really based on the Rosen-GRE that we have covered. So it is called Rosen-mLDP. It is also called Default MDT-mLDP or MDT-mLDP. But really, what it's trying to say is it's using a lot of components that we already learned about in Rosen-GRE or Profile 0, and it's just bringing it to an MPLS transport. Now, with that in mind, the CPIM does not really change. So CPIM is still CPIM. We're still using CPIM to communicate between the CE and the PE. We are also still overlaying that CPIM on the provider core. So we are not changing that. We are still going to encapsulate the CPIM packets and somehow get them across the provider core. How we do that encapsulation and how we tunnel them across the core, that's the biggest change, because now for the transport we are going to use MPLS. So we are going to use MP2MP LSPs for the signaling. Sometimes we are going to use P2MP LSPs for the data, but the transport is going to be totally MPLS based and not GRE based as it was earlier. So that's the biggest change. In order to facilitate that change, we somehow also have to do the signaling. We have to signal these MP2MP LSPs. And for that core signaling, we are using mLDP. So these three components combined basically bring all of the benefits of Profile 0 to Profile 1, but with the added benefit of using MPLS as a forwarding mechanism instead of IP. Now that we've talked about the various components that are needed, let's go ahead and build this particular network using Profile 1 this time. So what are some of the prerequisites, and then what are some of the configuration steps? The number one prerequisite is that the VPN v4 between the sites must be fully working. So there cannot be any lapses in that. And the major reason for that is multicast routing protocols use unicast routing tables for their RPF checks. And without the RPF check, the multicast routing, at least PIM-based, cannot function at all. So all of the PEs must have the VPN v4 routes in their VRFs, and that's what they are going to use to do the RPF checks. But furthermore, all of the sites must have these routes redistributed as IP routes. So they must know which interface to go out to get to certain sources or to get to the RP and all of that. So VPN v4 must be fully working. And in our particular network, it already is. We'll verify it, but I can assure you that it's already working in our particular network. The next thing, and this was in profile 0, there was a little bit different flavor of it, and that basically said that PPIM must be fully functional and configured. In this case, remember the transport is MPLS, and then the core tree protocol or the core signaling protocol is MLDP. So the new requirement now is that MLDP must be fully functional on all of the core routers. So at least the routers that are going to forward multicast, usually going to be all core routers. This must be ready to signal those MP2MP LSPs that are very, very important, and it must be ready to signal them end-to-end. So let's go ahead and verify that we have met our prerequisites first. So for the prerequisites, let's go ahead on some of the client sites. Once again, this is the topology that I will be using. There's a link available to it down in the description box below. Please download this and so you can follow along. But the very first thing is we're going to check the VPN v4 and if it is fully configured. I'm just going to do some very, very basic checks, and those are going to be the first one. I'm going to go to R7 and I'm going to ping both R9 and R10, and actually that's going to be it. I'm also going to run some trace routes, and what I want to see is that the pings are using the MPLS cores, the trace routes are using the MPLS cores. I don't have any backdoor links, for example, and that's what we are going to verify here. So let's go ahead and quickly verify that. So here I am on R7. And R7, let's go ahead and ping 10, 10, 10, 10. So once again, all of the loopbacks are basically in the form of XXXX. I know it doesn't really make much sense, but it keeps the video a little bit simpler to demonstrate. So in this case, R7 is 7777, R10 is 10, 10, 10, 10. These are loopback addresses, and they should be able to ping each other loopback to loopback. So 10, 10, 10, 10, source loopback 0. So there we go. We have sent a ping across, or 5, and we've received echo replies. We're also going to ping 9999 and also source it off loopback 0, and that's working. So the next thing to see here is the trace routes. So we are going to trace 10, 10, 10, 10. I'm going to source it from loopback 0. And as you can see, it is using the MPLS core. It is going through routers 1 to 3 to 4 to 22, which is XR2, and finally to router 10. So if we look at it from 1 to 3 to 4 to 22, so the ping goes out, and the first hop in the router is R6. So it goes from R7 to R6, over to R1, then to R3, then over to R4, and then finally it's going to be passed off to the other site, site 4, and finally going to arrive at R10. So we'll say trace 9999 source loopback 0. And once again, you can see that it goes from router 1 to router 2 to router 4, then down to XR1, which is router 21, and then to 8, and then finally down to 9. So unless until there is something really small missing somewhere, which we can fix along the way, the VPN v4 is completely working. The next thing here is going to be to get MLDP to work. But just remember that MLDP by default is already working on all of the iOS routers. So the classic iOS, IOSXE routers, it already works by default. If LDP is configured, then MLDP is also by default configured. That leaves us with XR. And with IOSXR, there would be one extra step that you would need to perform to get it to support MLDP. Let's go ahead and take a look at that. So here on XR1, which is iOS, which is the PEXR. So XR1, that's where we would need to configure MLDP. That's the only XR in our SP core that we need to configure MLDP on. And the command for this is going to be pretty straightforward. MPLS LDP, and then you choose MLDP. That's all you need to do. So we're not going to configure any parameters of this. Actually address family IPv4. So never forget the address family for whenever IOSXR is concerned. But in this particular case, there's only one address family supported. So MLDP for IPv6 is still not supported on IOSXR. But this is going to be the minimal command. And once this is here, that's configured, just commit the configuration. So now MLDP is also working on XR. It was already working on iOS. So we have in essence met all of our prerequisites. So let's go ahead and take a look at what needs to be configured now. So the first thing is we need to configure CPIM within the PEVRFs. So within the PEVRFs, they still need to exchange that CE information, the multicast state information between PE to CE. So on all of these routers, R1, XR1, and R4, what we are going to do is we are going to configure on these interfaces, here, here, and here, the PE to CE interfaces, we are going to configure VRF aware PIM, and this is going to be PIM sparse mode. So VRF aware PIM sparse mode is going to be configured in all of these. It's a little bit different way of doing things between iOS and IOSXR, as is always the case. So let's go ahead and take a look at how we are going to go ahead and do that. So let's start out with R1. Let's go ahead and start out with R1. And first up, let's see which interface is connected over to R6. So we can say show IPVRF, and that should tell us it is gig 2.16. So in this case, it's there are two steps to this. So in addition to, so for example, to get PIM sparse mode to work, we also need to configure multicast routing to work. I'm not sure if I have that as one of the steps here. Let's take a quick look. I do not, but in order to configure CPIM on the PEVRFs, you also need to do multicast routing. So the VRF also needs to run multicast routing on it. So the first thing we're going to do is on R1, we're going to say IP multicast routing. And now we are going to run it within the VRF. So VRF C1. C1 is the VRF that I'm using for all of these sites. So that's going to be constant. And a lot of times it's going to be distributed multicast routing. If it is not distributed, you could just say IP multicast routing VRF C1. If it is distributed, it won't let you configure the command without the distributed keyword. The next thing then is to go under this interface, gig 2.16, and just say IP PIM sparse mode. Since the interface is already under a VRF, it is already under a VRF, the PIM sparse mode works for that VRF alone. So the next thing you should see is you should build a neighbor relationship with the CE router. In this case, it is R6. So out here, I would see that there is a CPIM now working between R1 and R6. So this particular message, this PIM VRF aware PIM message, pretty much tells me that. So if I say do show IP PIM VRF C1 neighbors, I should now see 60.1.6.6 as a neighbor. Now, one thing I have not mentioned here is that R6 also happens to be an RP. So it is an RP in our customer sites. And eventually it's going to be the RP for all of the sites. And we are also using BSR to get this information across to all of the other PIM connected routers. So on R1, I should now be able to see an RP mapping. Let's go ahead and see if that is true. And usually if you see this message just coming out of nowhere, you haven't made a tunnel 0, that usually means a registration tunnel has been set up. So if I say do show IP PIM VRF-C1 RP mapping, I should now see that 6666 is a valid RP for me, and it is for the entire range 224/4. So that whole class T, I have an RP for it. So on R1, things are looking really good. Let's move over to R4, and it's going to be exactly the same thing. The first thing, get the multicast, the VRF aware multicast routing enabled. So IP multicast routing VRF-C1 distributed. And the next thing is to configure PIM sparse mode on the actual interface. So do show IPVRF, and on interface G2.422, we'll say IP PIM sparse mode. And we should see something similar pop up as it did on R1. And I have a new neighbor. This is neighbor 22, which happens to be XR2. And the DR has changed. So if I say do show IP PIM VRF-C1 neighbors, I should now see XR2, or rather 22, as a neighbor. So everything looks good here as well. That means now we have CPIM that runs between two of my sites. So two of the PECEs. Now there's going to be no RP information here because we have this whole vast MPLS network in the middle that is not transporting multicast, but that is what we are here to fix. The last step then is going to be on XR1. So we have to get this CPIM working. It's obviously always a little bit different with the XRs. So let's go ahead and see what it's going to be on in this case. So in XR1, most of this is going to be done from a inside a single hierarchy, and that hierarchy is the multicast routing hierarchy. So first go into the multicast routing hierarchy and then configure that for the VRF. So in this case, VRF is C1, and the next thing then is going to be to start that multicast the multicast routing for address family IPv4. And in this case, we don't really need to go interface to interface. There is one single command available that basically takes all of the IP interfaces within the VRF, or if you're out in the global hierarchy, for all of the global interfaces, and it can enable PIM sparse mode on all of those interfaces. And that is this interface command. So address family IPv4 interface, and I'm going to say interface all enable. And once I commit this, that should be all that is required. Now, I don't think I have logging configured on XR1, so I'm going to confirm this on R8. If I say show IP PIN neighbors, so this is not VRF aware on the CE side, I see that I now have an adjacency with 60.8.21.21, which happens to be XR1. We can also verify it here via show command. So we'll say do show PIM VRF-C1 neighbors, and I see that 60.8.21.8 is a neighbor. So now we can see that CPIM within the PEVRF completely configured. So we can move on to step 2, which is going to be to configure something called a VPN-ID. Pick a common VPN-ID, and that then has to be configured under the VRF of every single PE that takes part in that MVPN. Now, going back to MLDP, realize that MLDP needs two pieces of information to bring in LSP together, bring all of the branches of an LSP, MP2MP or P2MP LSP together. The first thing is the root. So where is that LSP going to be routed? But the second thing was that opaque value. And that opaque value was an arbitrary value. In case of profile 1, that arbitrary value is going to be created from this VPN ID. So as long as you configure the same VPN ID on all of your PEs, they are going to do the same process on that VPN ID to create an exactly same opaque value. So now you have a common opaque value for all of these PEs, and when they start signaling their MLDP FEC, the middle hop routers between them and the root, they're going to realize that because of the opaque value in the context of the root, which we're going to define next, all of these PEs want to join the same MP2MP LSP. Now, this is defined under the VRF, and that's true for both iOS and IOSXR. So let's go ahead and take a look. So first we are on iOS. Let's go to R1. And I'll say do show run VRF. And I have a VRF defined that is VRF definition C1. So I'll go inside that VRF. And I'll say VPN ID. And I'll pick one VPN ID. Now this essentially follows the same format as the RD, or you can use the same format as the RD. So I believe I can use the same thing as the RD. It may actually be more like the RT. So yeah, it doesn't take the RD value, but I can use an RT value here. So I'll say 100, 100. But as long as you stay within the realms of this, 3 bytes OUI and 4 bytes VPN index, and then configure it exactly the same on all of the PEs, it really doesn't matter what this value is. But this also provides you one more scalability factor. Instead of, as one of the Cisco live presenters said, instead of creating like a spreadsheet and then keeping a spreadsheet handy to see which VRFs are mapped to which PPIM groups, now you basically create a VPN ID, which could be, maybe the same as the route target. So everybody who needs to take part in that VPN, just go ahead and configure this VPN ID, and the rest pretty much takes care of itself. So R1 is done. Let's quickly do this on R2 or R4. So I'll say VRF definition C1 and VPN ID 100, 100, and finally on XR1, which will be VRF C1. Nope, I'm inside the multicast hierarchy, that's why. So VRF C1, VPN ID 100, 100, and then here I would commit. So that's the second part done. So now we should have a common opaque value for those LSPs to be signaled. The last thing here then is to select the MP2MP LSP route. So again, remember this is an MDT concept. So you're still doing that emulated LAN thing. You're treating the you're treating the provider core as a LAN or an emulated LAN for the customer. So we still need to signal an MP2MP LSP. And an MP2MP LSP needs an LSP route. So in this case, only IPv4 addresses are supported because we only still support IPv4 based LDP and MLDP. And this would be under the VRF definition, again in iOS. So it's the same old place where you configured profile 0. And the same thing applies to IOSXR. So there we configured profile 0 under multicast routing VRF. And that's the same place where this is going to be. So let's go ahead and configure them. So on R1, we're already under the VRF. So we'll go under address family IPv4 unicast. And here you'll have to say MDT. What are you configuring? You're configuring a default MDT. And that default MDT now is no longer GRE based, it is MPLS based. So default MDT default MPLS. MLDP is what we are using essentially. There's no other options right now. And finally, this is going to be a MP2MP LSP. So we are not dealing with the data MDT yet, but we are just doing an MP2MP LSP, which is the default MDT, and all I have to do is provide a route. So let's go ahead in our network, identify who can play a good route. And for that purpose, I think our RP used to be R3. So this was the RP back when we were doing profile 0. So I'll choose this as the route for the MP2MP LSP. So R3 is going to be the route for our MP2MP LSP. So I'll say 3.3.3.3. And there we go. So something similar now would have to be done on R4. So again, address family, IPv4 unicast, MDT, default, MPLS, mLDP, and then the address, which is 3333. And this is going to start that signaling as well, because that was the critical data that mLDP was waiting for. So once it has the opaque value in the form of the VPN-ID, and once it has the route that it needs to signal the MP2MP LSP to, it can go ahead and finish the signaling of it. Now on XR1, there is something that you need to be mindful of. So let's first go ahead and provide it all of the other information, which is basically the route of the MP2MP LSP. That is going to be under multicast routing, VRF C1. And here you would again say address family IPv4, MDT, default, and there are more options available, but we're going to go with mLDP. IPv4, because we need to do an MP2MP core tree. That's what we are doing. And then the root address here is going to be 3333. And I would say commit. But this, I believe this is not all that is needed, unfortunately, in the case of IOSXR. So to illustrate that, let me first go to R1. And I am going to say, and already you can see, just like profile 0, we are making neighbors across the MPLS core. So this in particular is router 4, that PE. And that is now adjacent on CPIM. So we are aware PIM with R1. So that's a good sign. But if I say do show IP PIM VRF C1 interfaces, I do see that other interface, the LSP VIF interface that was created by mLDP, and that's basically what the logical gateway is for that MP2MP LSP that we have created. You can see it is part of the CPIM. Same thing on R4. So if I say do show IP PIM VRF C1 interfaces, that LSP VIF interface is part of the CPIM. In case of XR1, you would realize if I say do show PIM VRF C1 interfaces, even though this they decide to call it something different, it's not called LSP VIF, it's called LMDTC1. So LMDT being I'm not sure about L, but this is MDT, right? Multicast distribution tree for VRF C1. But if you notice, PIM is off on it. So there's one more thing, and I think we ran into this with profile 0 as well, but there's actually two more things that are going to be needed. The first thing with iOS and IOSXC, when they signal that MP2MP LSP, they go by the update source configured for BGP VPN v4. So in this case, for R1, if I say do show run section VPN v4, or No, sorry, not that. I would say include neighbor. I am using an update source of loopback 0. So that is the same source then is used for the default MDT, whether it be profile 0 with GRE or profile 1 with MLDP. With XR1, it doesn't pick it up by default. So you need to supply it manually. So let's go ahead and do that. So right now, if you look at the address, it's 0000, whereas on R1, it's 1111, and on R4, it's 4444. So that's our first problem that we need to solve. So we would say MDT source, and then just provide the source. So this is loopback 0. MDT source loopback 0, let's say commit. But that, I believe, is still not going to solve our problem because there's one more configuration piece that we are missing. So let's say do show PIM VRF C1 interfaces. Now we do have an address for it. So that's a good thing. We have an address for our LMDTC1 interface, but look at this. PIM is still off. So as long as PIM is still off on that particular interface, that means I cannot create neighborships with my PEs that are across the core. And how do we fix it? Well, this is something you would have to remember because I don't really think it's even covered in the documentation. If it is, I just basically missed it. But in this case, what you have to do is you have to go to this interface, which is LO0 in the global context, and you have to bring it into multicast. So even though we are not running any PPIM here, this doesn't mean I'm running any PPIM. It just essentially is another step that is needed to make that interface participate in multicast. So we're not participating in PIM sparse mode, we're just participating in multicast. So let's go ahead and see how we're going to fix it. So I'll just go to multicast routing, address family IPv4. So notice I did not go into the VRF this time. This is in the global multicast context. And I would say interface loopback 0 enable. And once I say commit here, hopefully this is going to solve my problem. So let's look at the PIM interfaces. And now you can see I am 21, 21, 21, 21. So we solved that problem. And PIM is now on it. And we have a neighbor count of 3. Why 3? Because XR always considers itself a neighbor. So what I'm assuming is R1 is a neighbor, R4 is a neighbor, and then XR1 considers itself another neighbor. But let's take a look at it. And there you go. R1, R4, and then XR1 considers itself another neighbor on that LMDT-C1. Well, but what does that mean? That does mean that our core right now should be functional. Because think about it, what have we done? We have a CPIM neighborship that now exists between R1 and R4. We have a CPIM neighborship between XR1 and R1. And finally, one between R4 and XR1. So essentially what this looks like now is an emulated LAN with all of the routers adjacent with each other. So all of the CPIM messages that originate in the sites should be able to travel across this overlay and get to the various sites wherever they need to. How do we test this? So we're going to test this pretty simply, and we're going to try to involve all of the components in the testing. How the MLDP actually is working probably is going to be covered in the next lecture, but in this one, let's just go ahead and verify that we have gotten our core to transit multicast. And what will we do? So let's go to R9, which sits in the side behind XR1, and R9 here so R9 should be, let's say it's a receiver. So it's a receiver for 239.1.2.3 because, why mess with perfection? And then R10 up top behind the site in R4 or site behind R4 can be the source for 239.1.2.3. And both of these are C multicast groups. So keep that in mind. So once we do that, then we can, if R10 can reach R9, then we have succeeded in doing what we wanted to do. So let's go ahead to R9. And we'll say interface loopback 0. And I'll say IP IGMP join group 239.123. So let's see, do show IP IGMP groups. So there we go, 239.123 on loopback 0 is now configured, it's listening. That's good. On R10, what do we need to do? We need to send simple pings. So we'll say ping 239.123. We'll say source loopback 0. Let's give it high repeat count. And this does not look like it's actually working. So obviously there's going to be maybe some troubleshooting steps here in our future, but let's try to check a couple of things. So if R10 is sending these packets, what is the first thing that should happen? There should be, so if R10 is sending this, what should happen is there should be a unicast registration message that should go out to the RP 6666. So at that point, if it's just registration, we should at least see the registration on R10 and also on R6. So let's go ahead and check on R6 if we see a registration message here. So I'll say do show IP mroute 239.123. And I definitely see a registration message, so that S, G has made it all the way. But what's the problem here? Well, one that's staring me in the face here is that the outgoing interface is null. So I know where the incoming packets may come from. I've done an RPF check on the source, and that's fine. But I don't have an outgoing interface list yet. So, and I also don't have it in either one of the states. So not star, G and not S, G. Not having it in S, G is okay, but not having it in star, G means I may have never gotten the initial join that should come from R9. So let's go to R9 and see what the problem is. So we can say do show IP mroute 239.123. And here's the problem. There's no incoming interface at all. There's an outgoing interface list because of the IGMP join, but there's no incoming interface list for this star, G tree. Now, where should a star, G tree be signaled towards? Has to be signaled towards the RP. So that's obviously a problem. I don't seem to have an RP mapping, at least for 239.123. Let's take a look. Do show IP PIM RP mapping. And sure as the day is long, there is no RP mapping. Let's check upstream. Let's check on R8. So this might have to be dealt with on a hop-by-hop basis. So we'll say show IP PIM RP mapping on R8. And that also shows me an empty RP mapping. Well, finally, I have to go to XR1, right? So XR1 is my upstream. And I'll have to say do show PIM VRFC1, and the command here is range list. And that's the problem. So I am not getting anything on XR1, nothing populating my RP on XR1. Well, at this point, I think I know what the problem is. But in case you run into this problem, especially like in the CCIE lab and you forget about this, let's think about how we are going to do it. So we could run some debugs. Obviously, those messages. So how is R6 disseminating this information? R6 is going to disseminate this information using BSR messages. And what are BSR messages carried in? They're carried in PIM. So PIM is definitely getting across the core, but for some reason, BSR is not getting carried across with it. That's the problem. The PIM is getting carried, and that I know because I'm making this CPIM neighborship here. But BSR is, for some reason, not going through. So let's take a look at how we are going to do this. And I think one of the ways to do this would be a debug. Now for a debug, I don't think I have logging enabled on it here. So let's see, nothing in the logging. So let's enable logging on the console at debugging. Let's commit that. And now we can say debug PIM. It'll have to be in VRFC1 and BSR. So there's a BSR debug that we can do. So this may take a couple of seconds here. Let's see if there's any other debugging that we need to do. So one thing I want to show you in the meantime is R4 is definitely getting that BSR message. So if I say do show PIM or do show IP PIM, VRFC1 RP mapping, you can see that the other PE, the IOSXRProfile, is getting that BSR message. It's processing it, it's passing it down to the site. So there's a problem with XR1. And here, I believe this is the message that I'm looking for. Let's undebug this. And what's the problem here? So it received a BSR message from 1111. It tried to do a BSR RPF lookup, and it's dropping the BSR message from 1111 because the RPF has failed. The expected RPF neighbor is 0000, and the expected interface was null. Well, here is where XR's RPF lookup is also different from XE. So we didn't run into this problem with profile 0 because by default, the core signaling protocol that is being looked up for RPF has PIM and PIM alone. So as long as your core tree, which is the MDT, it was created using PIM, you are fine. And there's really no way to verify it. I've looked at different places to see if I can see the default, but there's no default that is visible unless you guys tell me in the comments, and then I can update the lecture with it. But what it's trying to do is it's only trying to verify using PIM created trees, not MDT created or mLDP created trees. How will we change that? It's a bit of a process, so you would have to remember this. It's under PIM, so you would say router PIM VRFC1. And then you would say address family IPv4, obviously. And then it would be this RPF command. RPF topology, so which topology or which core tree to use. And as you can see, it takes a route policy. So let me give it a route policy name, and then we'll go ahead and create the route policy. So I'll say RP PIM RPF. Why not? And that should be it. So to create this policy, you'd create the policy, you'd say route policy, RP PIM RPF. And what you have to now do is you have to set the core trees. That's what they call that RPF check. And the database it's using for that RPF check, it's called the core tree. And our core tree happens to be mLDP default. So there we go. As long as we create this policy and we apply this policy to the PIM RPF topology, I believe we should be fine. So we'll say set core tree, mLDP default, exit out of the RPL, and now let's try to commit. And it looks like it took the commit. So if I haven't already lost the message, let's debug this again and also do show PIM VRFC1 range list. Okay, so the message hasn't come yet. It's going to come at the hello interval, basically. It's carried in the PIM hello, or I believe it's carried in the PIM hello, but it's a timer-based message. And now look at it. There's much more that's happened here. I see activity that's also happening on my site internal devices. So this actually looks pretty good. Let's say undebug all. And let's look at this. So PIM BSR update, BSR lookup info. There was no state before. Now it's 6666. BSR address. The RPF update. I'm trying to see if it's going to. Well, you can see that it is accepting that message, but it's not saying where it's doing the RPF lookup. But essentially, it accepted a message of 6666 on interface LMDTC1. So now if I say show IP PIM range list, there we go. Now I have an RP for that, class D, which is 6666. So what about on R10? R10 was already done, so let's start these pings again. And there we go. So now I'm getting responses from 9999. And if you look on R6, I also see the star comma G tree that has been completed. So there's no incoming interface because we are the root and star comma G trees end at the root. It's a rendezvous point tree. The outgoing interface list has that interface towards R1, so back towards the core. So the only problem there was that XR1 was not accepting any BSR messages. It wasn't creating the RP mapping, and it wasn't disseminating that information further beyond into Site 21. Once we resolve that issue, everything seems to be working. Well, that took some time to configure all of the pieces, especially on XR, which can be a little bit involved. But in the end, we have a functional SP core that is running Profile 1. We proved that with our pings. Well, in the next video, we will understand and verify the operation of MLDP in the core and see how it goes about creating these MP2MP LSPs and what do they look like on the P routers, on the PE routers, all of that. Till then, I would like to thank you for joining us and urge you to stay tuned for our next video. Thanks.